Good evening, everyone. I'm Deb Henneberry of the 99's Webinar Committee, and I welcome you to tonight's presentation, Clouds, Winds, and Weather Theory with Veronica Cote. I'd also like to take a moment to thank the sponsor of tonight's webinar, SiriusXM. And now I will hand things over to Glenda.
Thank you, Deb. Welcome, everyone. I'm Glenna Blackwell, currently serving as the 99's International Secretary. Please help me in welcoming Veronica Cote this evening. Veronica is our weather guru. Veronica, tell us a little bit more about yourself. We're very thrilled to have you with us this evening.
Thank you. Veronica Cote. I'm Associate Professor at Bridgewater State University. I'm a member of the 99's and EAA and AOPA and Women in Aviation and NAFI and SAFE and International Society of Air Safety Investigations, and of course a proud member of the Cloud Appreciation Society, which I will give you some information if you care to join. It's a fantastic group, and if you love clouds, like we're all pilots, so we all keep looking up, I think you'll enjoy it. So why study clouds? Well, as pilots, we look up in the sky all the time, and we should know that, the clouds will give us some idea as to what the atmosphere is doing. And of course, clouds are beautiful. And so we'll cover the 10 distinctive cloud types, what they're, how they're made and how they're formed. And we'll look at some interesting optical effects at the end. And again, if we pay a close attention to the clouds in the grand scheme of things, with looking at our regular weather products, our surface analysis chart and our Metars and TAFs and all the other great products that are out there, we should be able to do a pretty good job of figuring out what the weather's going to be like upstairs. Again, clouds are never static. They change quickly and over a short period of time. And so we have to be aware of what's going on. So what is a cloud? Merely a collection of tiny water droplets or ice crystals suspended in the atmosphere. But the important thing is, as we know, is water vapor has energy. And this energy in the atmosphere fuels the weather. So when we read our private pilot test bank, it says, the first one they ask is, what is the driving force of all weather? And we answer, uneven heating of the Earth's surface. And we learn that rote question and answer. But when we start to delve into it a little bit more, we see that all weather is energy and heat exchange. And how it happens varies a little bit on what part of the atmosphere we're talking about. So it is heat and energy, but in so many different ways than just the sun hitting the equator, a little bit differently than it does up here at 42 degrees north. All right. So we have to understand the energy that's in water vapor. So we know that water vapor is always present in the atmosphere, and the potential amount of water vapor depends on the temperature of the air. The warmer the air, the more water vapor we can hold. So, and how much actual volume of water, how much actual measurable grams of water depends on the temperature. And we have to define a dew point. So dew point is the temperature to which air must cool for the water vapor to condense. And so is it condensed as a cloud or dew or frost or snow crystals or any other such whatever we have for water vapor to condense. And of course, that depends on temperature and the in the processes of temperature. Okay, so how is a cloud formed? By cooling the air to the saturation temperature or by adding more moisture. We have to get to 100% saturation and sometimes supersaturation in order for that water vapor to appear from the air. So we need to cool it or supersaturate it so we can actually see it. And in meteorology and weather, we classify clouds as families. So here's the FAA test bank question. The families are low, middle, high, and extensive vertical development. And the shapes or types are cumulus, stratus, and cirrus variety. So we'll look at examples of all of these and how they're formed and what they can tell us about what's going on upstairs in the sky. So here's that wonderful 10 major cloud types. So we see the cirrus clouds up top, the alto is our middle clouds there, and our low clouds, our stratus, are fog type clouds. And believe it or not, a cumulonimbus is considered a low cloud because we're talking about the cloud bases. And it can go all the way up to the top of the atmosphere. So the old expression, I'm on cloud 9, and 9 was the highest level of, actually 8 is the highest level of cloud. So if you're on cloud 9 back in the day, then you were, above the highest level of cloud, feeling good. So we'll look at our shapes, our cumulus, our stratus, and our cirrus shapes. And here's our little bit of meteorology, our little weather theory stuff. So we have to go through here. So here's our water cycle. And if you're ready, you can sing it with me, the water cycle song, so we don't all forget. So join in at any time. And here we go. Water travels in a cycle, yes it does. Water travels in a cycle, yes it does. It goes up as evaporation, becomes a cloud with condensation, and comes down in precipitation, yes it does. Everybody! See, now you'll never forget the water cycle. My son taught me that in 3rd grade and I never forgot it. And it's a good lesson for all of us. And we know that water changes state. So we can have water in a gas form, the vapor form, in an ice form, or in a liquid form. But every time, here's the key, every time water changes or water vapor changes from a solid to a liquid to a gas, there's energy exchange. We have to add a lot of energy to ice to have it melt. We have to add even more energy from water to make it a vapor. And then when the vapor condenses back to a solid or a drop, then that energy that was taken from the atmosphere is given back out into the atmosphere. So there's always energy taking place all the time. So cloud drops versus raindrops versus drizzle drops. So size really matters. And we're going to look at it. Cloud droplets are really, really tiny. There's a lot of zeros there after that decimal point. They're not heavy enough to overcome the updrafts. A cloud drop, therefore, is 1,000,000 times larger than the nucleus. So the nucleus is really tiny. And cloud droplets grow on condensation nuclei, such as dust or salt spray or any other pollutions in the atmosphere. And then we need 1,000,000 drizzle drops, 1,000,000 cloud droplets to get a drizzle drop. And when they collide, they form much larger droplets. So here is a kind of sort of to size scale of a haze drop. You can see over there the condensation particle right over here in the corner. So it's really this teeny tiny dot there. And then there's a haze, a cloud drop, a drizzle drop, and then about the average of a raindrop. As the raindrop is falling, of course, it doesn't look like that beautiful round drop that we see, or the typical picture we see is a raindrop. When the raindrop is actually falling, it's more like a mushed hamburger shape because it's facing the resistance as it's falling down. So here's the other part of our weather theory we have to go through. We have to talk a little bit of what's called parcel theory. And so this is all about energy taking place. So the theory is in meteorology that a parcel of air can be any size. So we're talking about a theoretical parcel that starts at the surface and is lifted somehow. And as that parcel is lifted, it's going to retain its original moisture and heat content versus the environmental temperature, which is the environment outside the parcel. So as the parcel is being forced to rise through to just straight up physics, it's going to expand because the atmospheric density is less. And when that parcel expands, it cools. And then if the parcel is still warmer than the environmental temperature, it'll continue to rise. So it really depends on, again, this is another example of temperature. What makes weather is differences in temperature. In this particular case, it's the difference between the temperature of the parcel and the temperature of the atmosphere. So what we call the dry adiabatic lapse rate, when the temperature, let's say the sun's heating up as part of the town, let's say at the airport. And of course, we know that the parcel that's over the ramp or the runway, because it's going to absorb more energy because of the black top, it's going to heat up faster. and it's going to rise faster. And as it rises, it's going to expand and cool. Well, at some point, the air is going to rise, and let's say it's warmer than the environmental temperature, and that parcel eventually cools to the dew point. Well, when it cools to the dew point, then that water vapor will become visible. And when it becomes visible, we'll see it as a cloud droplet. If the dew point's on the ground and the air cools at night to the dew point, then we'll see it as dew on the grass, or if the dew point's below freezing, we'll see it as frost. So the buoyancy of the parcel depends upon how quickly, or the temperature difference between the parcel and the environmental temperature. So we'll go through this a little bit more. So here's a nice picture of this here. So there's the surface temperature right there and the dew point right there they've given us, and there's that cubic block of air parcel. So that air parcel is going to be warmer than the surrounding temperature, so it's going to rise. And so as it rises up, it expands, it cools a little bit, and it's going to continue to rise until we get to the dew point, and at that point we'll begin to see the cloud droplet. So the point where the temperature and dew point meet, the meteorological term is called the lifted condensation level. When it happens at the surface, we call it the dew point, but it's essentially the same thing. That's where the temperature cools so that the water vapor becomes visible. Once the water vapor becomes visible, that parcel will rise, but at a slower rate, because the energy that's released back into the parcel when it cools to the dew point and that water vapor condenses, that little bit of energy that it took to make that liquid become a gas in the first place, that energy is released to the atmosphere. And so the actual moist adiabatic lapse rate is going to be a little bit somewhat slower than the dry adiabatic lapse rate. So this is one way. This is the adiabatic process, just the expansion and cooling of air. And we can see the adiabatic process in a number of different ways. So for example, when you open up a nice cold Coca-Cola on the summer day, and you pop the top and you hear that, psh, and then all of a sudden the neck of the bottle might get a little cloudy. Well, what happened is release that pressure, it cooled to the saturation point, and then we got basically a baby cloud inside the bottle. So that's one example of that. So a lapse rate, how much the temperature cools per 1,000 feet. That's what the lapse rate is. It's a change of pressure or a change in temperature. So any given day, the actual environmental temperature really matches the static one, the given information. So the actual environmental temperature that's what's measured by those balloons that I take twice a day at 1200 and 2400 Z all around the world when they release those environmental balloon, the soundings. That's some of the data that goes into the actual environmental temperature. And that's some of the data that goes into those super duper computers that gives us all these wonderful forecasts. So in unsaturated air, the rapid rise of the parcel is called dry convection. So normally we think of convection as it's a vertical movement of the atmosphere. So when we put a pot of water on the stove, we see that convection current as the water down on the closer to the stove starts to heat up and boil, it'll start to raise up, and we have that convection current. So what we have is, depending upon the temperature of the environment, we can have a large lapse rate. In other words, how quickly does it get cold? One of the test bank questions that they ask you is the stability of the atmosphere. What determines this, or how does you make the atmosphere unstable, or something to that effect? And the answer that they want in the test bank is warming from below, which makes the atmosphere unstable. That's only partially true, or it's not the whole answer. It's not just warming from below. You could have warming from below, but you can have the air trying to rise into a temperature inversion, and consequently it's not going to rise much. So all the warming from below is not going to help if there's an inversion. What really makes the air unstable is how cold is it aloft, and how quickly does it get cold aloft. That adds to the instability of the atmosphere. So it's a combination of both warming from below and giving that parcel a place to go when it rises, to rise and expand. So here's an example on the left-hand side. If the parcel temperature is warmer than the environmental temperature, the parcel will continue to rise. And the greater the difference here is going to be the greater how quickly the parcel is actually going to rise. So on the left-hand side, we see here that here's the surface temperature, and notice the parcel temperature right here is 20 degrees, the surface is 20 degrees. As the air is forced to rise, it cools, right? But in this particular case, the environmental temperature is pretty stable. It's not cooling at 3 degrees C per 1,000 feet. It's only cooling at 1 degree C per 1,000 feet. So the temperature over here, it's going to be very stable, and it's not going to rise very quickly. Whereas over here on the right-hand side, we see how quickly the temperature is cooling with altitude. So it's 20 degrees C at the surface, then 16, then 12 degrees. So this parcel temperature, parcel and dew point temperature, as it starts to rise, it's unstable because it's cooling rather quickly as you go up. So this parcel temperature is still at 7 degrees here, is much warmer than the environmental temperature. And so we'd have to think about, all right, under what conditions would the environmental temperature be colder than the parcel temperature? And if I were in class, I would open this up and say, what would make the difference? Well, we'd have to consider about, frontal systems. So here is another picture. This actually comes from one of my resources that I want to give a shout out to right away, and as often as I can, is one of the best books you can get on weather. It's by Scott Deadstead and Jeff Morris. It's called Pilot Weather from Solo to the Airlines, and he published it a couple of years ago. It is the best weather book out there for pilots, and I have my students buy it, and I go back to it over and over and over again. And he gave me permission to use his slides, giving him credit, and I give him all the credit in the world. So this is a picture from his book about the air parcel rising at the dry adiabatic lapse rate to the lifting condensation level, and then it's going to rise at the saturated adiabatic lapse rate, and it's going to be much slower. We talk a lot about, or the PHAC, I was just rereading the PHAC again. They talk about an average lapse rate of 2.5 degrees C per 1,000 feet. Well, what they're counting in that particular case is the dew point lapse rate. The dew point lapse rate is 0.5 degrees C per 1,000 feet, so they average it out to get the 2.5 degrees C per 1,000 feet for the dry adiabatic lapse rate right there. So what causes lifting? Well, we have 4 different mechanisms that could get that adiabatic process going. One, of course, is convective, the one we're all familiar with. The air is warm, the parcel rises, it expands, it cools, then there's the downdraft, and then as the air is rising, some air has to fill in from the sides to take its place. So this is where we're going to get those fair weather cumulus and where our sea breezes or land breezes over here by the coast. We have frontal lifting. So like I mentioned a little bit ago, is if the air is being forced aloft by a front, well, if there's cold air behind it, then that warm air is going to be lifted into a colder environment, and that would cause instability. So it's lifting into colder and colder air, and that's going to give that parcel a chance to grow, and maybe grow very, very explosively if there's warmer air aloft or warmer air ahead of it, like we know, and warmer air can hold more moisture. And this is where we're going to get to the wicked weather of severe storm season across the plains and the Gulf as the months move on here. The other way we can have is air being forced to ascend over a mountain, over a ridge. So if you're on the lee or the downward side of any sort of mountain range, like in Colorado or the Sierra Nevadas, or even us here, our wicked high Appalachians, we have water vapor going up on one side, the air rises, expands, and cools adiabatically, and then the air parcel is all rained out on this side. And then we'll have the rain shadow area as the air is forced downwards. So as the air is forced down, then it heats adiabatically at that 3 degrees per 1,000 feet. And this, as we know, if you're out in the western states, you can have those very high Santa Anas and very strong Chinook winds, as these winds can come down and change the temperature dramatically over a course of a few minutes with these descending air. And of course, the last one we hear is convergence. So a convergence is quite simply air coming together for example, in a low pressure system. So alongside a stationary front, or I should say stationary front, air is moving in opposite directions. But once we get that sort of kink in the stationary front and the air starts to circulate because of the Coriolis force, then we have this convergence where the air is just meeting, mashing together, and being forced upward. And this upward convergence at the surface, this type of convergence, is our low pressure system. And as the air converges at the surface and is being forced aloft, right here, well, the air diverges at the top. Okay, so we have convergence at the surface and divergence at the top. Well, that divergent air goes somewhere, and what that divergent air does is it goes to the high pressure system that's following it, and the air is converging at the top and diverging at the surface. So this is how we get that counterclockwise and upward around a low, and that on the high pressure system we have it, the air is downward moving, right? It's converging at the surface and rotating in a clockwise direction. Stable atmosphere. So when the temperature increases with height, we call it a temperature inversion. So what causes a temperature inversion? So this subsidence inversion, what they're talking about here is a high pressure system that's coming in and slowly sinking air. So that's going to put a lid on cumulus clouds. So for example, in your basic run-of-the-mill alto cumulus cloud or stratocumulus cloud, where it may only be a couple thousand feet thick and it's not rising anymore. Why? Because there's a temperature inversion. So there could be a high pressure system there where we may have some air rising, cooling, condensing, but it's not rising anymore. And that's where a cumulus cloud, if it rises and then it hits that sinking air, that temperature inversion, it spreads out and you can have this sort of a very shallow overcast layer because of a stratocumulus that the air is rising and then spreading out because of the temperature inversion. Once again, we can have warm air creeping up on the backside of a receding high pressure. I know we talk a lot about fronts, cold fronts, warm fronts, but nobody ever talks about backs. So the back would be the back end of that high pressure system, the back end of that dome. So on the back of that high pressure system that's leaving, well, it's the warm air coming up or the next air. So it's sort of warm air rises. So it's creeping behind the receding cooler air of that high pressure system that's moving on. And of course, we have the nocturnal inversion, which happens basically every night. If you look at SQT diagrams, if you're familiar with them, you check them every morning. Almost always there's a nocturnal inversion. So the air cools at night. Well, the surface cools. Where's that warm air going? And it's going aloft. So it may only be a shallow temperature inversion, or it could be quite a steep temperature inversion, depending upon how warm the air was. Is it clear skies? Is there a high overcast? So there's almost always a temperature inversion at night. And of course, there's a tropopause inversion way up high, where the temperature starts to increase with altitude, way up in the 30,000 foot air. All right, so let's get back to the clouds. Now that we had a little bit of ground school about temperatures and lapse rates and air climbing, ascending and expanding and cooling, and how the environmental versus regular lapse rate, we can start talking about our families of clouds once again. So our families, low, middle, high, and extensive vertical, and our cloud types based on the shape. So again, low clouds, we consider surface to about 6,500 feet. And so for us, we're going to look at, that would be our low ceilings, right? Below 6,500 feet, we can have cumulus stratus, stratocumulus type clouds. The mid-level clouds, again, from 65 to about 20,000 feet, mostly water or ice crystals or both, depending, again, on the temperature. And the high-level clouds are cirrus or ice crystals and thin and white in appearance. And they're usually sort of fuzzy in appearance. That's because the high-level clouds, the crystals they look fuzzy to us from the ground, as opposed to a water droplet, which would give sort of a hard edge to the shape of the cloud. So again, unstable atmosphere is necessary. So that generates thermal turbulence for us. Taking off on a mid-afternoon on a sunny day is probably not the best time to take a novice flying because we know it's going to be bumpy. Stable conditions. When their air is not moving vertically, it's beautiful to practice low, ceilings. Or rather, if you have a nice low IFR day to practice, it's not going to get any worse. You're going to be smooth in the clouds, or sort of a stable air condition, stable air, the conditions of the air, the atmosphere. Nice, not very turbulent, but we can have types of fog. And again, knowing the stability of the atmosphere, will give us an indication as to what kind of clouds are going to develop. So this is the cloud species and varieties. So there's a whole taxonomy on this, like there are for, animals and, person in the animal kingdoms. Well, this fellow about 150 years ago figured out that he should start classifying cloud species. So he started doing just that. So our low clouds are generally made of water droplets, of course, unless it's, below freezing. A droplet has clear edges. And so our typical fair weather cumulus would be a cumulus or mediocritus, depending upon the shape, whether it's higher than it is wide or wider than it is high. And then we have a stratocumulus, which means it's got some puffy, but it's not building constantly. It has a lid on it. And if you have a nimbo associated with it, it means rain, or of course fog. So for us, the Metar ceiling would be an overcast or a broken cloud. So these are the types of low clouds we can get. And I'm going to spend a few minutes when we get there talking about fog here in a bit. But cumulus, those are our species. They're the humble little clouds, or the mediocre clouds, or congestus, meaning that we have that it's starting to grow and nothing's prohibiting the growth of that cloud. So that congestus can certainly grow into a cumulonimbus cloud. And then we have little accessory clouds depending upon its shape. And that's what those accessory clouds are. So here's some fair weather cumulus right here. Warm air ascends, expands, and cools adiabatically. We can see over here some little bits of virga maybe. Again, we know that this indicates this vertical movement in the atmosphere. So we got to be aware that this is where the temperature, or where the water vapor is cooling to the dew point. So there will be a bump when you hit that level because energy is taking place. And again, this is where, from a cumulus cloud, this is where our Metar is going to give us indications of showers as opposed to steady rain. So showers come from cumulus clouds. Rain, or the steady rain, generally comes from our stratus clouds. So here's our cumulus clouds. Again, our fair weather cumulus. Always when you're looking, you want to look at the what's happening above that. So let me go backward a little bit. So our fair weather cumulus, what's happening above? Well, there's not really a front coming in. So this is flying in over by the Great Lakes. So because the lake is very uniform in color, the air is pretty stable, rising at a uniform rate. But as we get further inland, we see that diurnal heating, that we have these puffy cumulus clouds coming up. And so this is just, downwind of the lakes. And we can see, you can imagine this in the wintertime, this being lake effect snow. If there's enough cold air and enough moisture, it's still going to pick up moisture of the Great Lakes as long as it's not frozen. And this is where we can get all that. And those of you who live downwind of the lakes know certainly well about lake effect snow. And this is interesting. This is called a radiatus. So this is flying over some, like the ridges of like the Appalachian Mountains down here. So the air is being forced aloft, right? And we can see it cooling and condensing. And then the air is being forced downward over here, and it's dry. And then the air is being forced upward again. And we have another long ridge of clouds being formed, and then the downdraft again. So you could expect, looking at this, where are the bumps going to be? Well, even though you can't see it, there's certainly going to be a lot of bumps associated downwind of these, because we know that there's a downdraft because we can see the updraft. Even though the downdraft is invisible, it's certainly going to be there. Again, cumulus clouds, flat bases, all the same. I see some high-level cirrus coming in here, so my guess is there's probably some sort of system coming in, and this may be warm air that's riding on top of a receding warm front, but this is certainly diurnal cumulus, sort of you can see how it might be even a castellanus as it's starting to rise up. So this indicates there's instability, nothing's capping that rise. So as we look up at our clouds, we're seeing few scattered or broken clouds over there. Okay, so there will be some sort of turbulence. So stratus clouds, we have, there can only be one species. It's nebulosus, which means featureless, or fractus, just little bits and pieces. So we can either see the sun through it, we can't see the sun through it, or there's some sort of wave through it. So that's just I never took Latin, so it's opaque or it's translucent. That much I can figure out. So here we are, not much vertical development. It's pretty straight. So here again, if our ceilings are broken or overcast below 5,000 feet, it's probably pretty likely it's a stratus cloud. And then we'd have to look at the rest of our surface analysis chart to see, yep, there's a front moving in, or there's a warm front here. So that's what's going to give us our stratus type clouds. And so here we see some low clouds. This air is very saturated, we can tell, because the temperature and dew point are very close together because the clouds are hugging close to the surface. So when the low temperature dew point, it won't take much for a cloud to form right here. So we know that this atmosphere has a lot of humidity associated with that, or high relative humidity. Okay, here's some practice clouds, some bits and pieces of clouds. Here is an opacus, the sun's not visible. Here is some panis and practice below. This was may run ahead of bad weather. So this is when I took at Oshkosh a couple of years ago. So we're looking over here with the temperature and dew point. The temperature is 2.2 and the dew point is 1.6. So if I did that standard lapse rate of about 3 degrees C per 1,000 feet before it saturates, it makes sense that my ceilings are about here because I have, 6 degrees difference. So it would make sense that this would be my fractus and maybe my broken. Again, that's using the standard lapse rate, but that's just a guide for the adiabatic. What's actually happening in the environment is what we have to pay attention to as well. Again, looking out to the west, I see some clouds lowering in the west. I see that these practice clouds are pretty low. So this is telling me that this atmosphere is getting more and more humid, getting more saturated. And certainly, sure enough, the next day, this is what the weather was like the next day at the air show. Thankfully, the ceiling was high enough for the folks to come out and do some of their aerobatics. And this was the TAF and the Metar. So this was the TAF. And again, when you call up a bunch of Metars, you're reading from the bottom up. And this leads me to one of my first never, ever, evers. Never, ever, 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 ever 5 or 6 evers. Never, ever, ever just get the first Metar when you're going flying. Always get a minimum of 3 to 6 hours because you want to know what the trend is. Because if we just did a single Metar, we'd get this. All right, that's an hourly. But looking back just an hour, look what happened. So we went from 1.25 to 10 to 10, and so we have a lot of action going on in the atmosphere right here, and our close temperature dew points right here. Something to pay really close attention to. Fog. Okay, stratus on the ground, super saturated. Fog is considered to be within 50 feet. And here is the difference in your Metar, whether you see fog or mist. As far as the cloud droplet goes, it doesn't matter. Fog is a visibility construct, not a cloud construct. In other words, when the surface visibility is a half a mile or less, then we call it fog. If it's more than a half a mile but less than 7, we call it mist. Okay. Example, we need high water content, close temperature dew point. We have to cool the air or add moisture, get it super saturated in order to get the fog. And this is looking out over Logan. So just right beyond that little fog bank is the harbor right there. Types of fog. I spend a little bit more time on fog because most people don't quite get it. Fog can get us into trouble real fast if we're not paying attention to it. So we know about vertical movement of convection. Advection fog is horizontal movement. So anything advection is horizontal. And the fog is basically a cloud on the ground, but it's defined by how it's formed. So advection fog, we have warm air over a cool surface. So that cool surface is going to cool that moist air that's right adjacent to the surface, and that's where we're going to get fog. We can get a fog bank. So this might be our fog over like the coast of like California, right? Or San Francisco fog. Radiation fog, where the surface cools at night. There's nothing to cap it, so that energy is going to go radiate all the way out into space, and the surface can cool in quite rapidly. Steam fog happens around here. I live on the Cape, Cape Cod, or anywhere in the lakes. If you were anywhere foggy conditions in the fall time, the water retains the heat more than the air. So as the air cools at night, you're going to get that sea smoke or that fog just over the water because that water is actually cooling the air to the dew point. And so that's how you're getting that the fog over the lakes and the bogs here in the fall time. Again, we talked about upslope fog, and ice fog happens when it's very, very, very cold. and then the precipitation fog. So let's take a look right here. So advection fog, again, when warm air goes over a cold ocean, or conversely, when cold air goes over something warm. And it can stay for a long time. So here we have our Pacific or our tropical air in the Gulf Coast. I see it around here in the Cape in the evening time in the summertime when it's pretty humid out. I look up and I see these fractus clouds, these little gray fractus clouds at about, I don't know, 1 to 200 feet coming in. And I call it tall fog because, you know, the temperature dew point's really close. It's going to be fog. It's going to be within 50 feet of the ground pretty soon. It hasn't quite got there yet. So I call it tall fog. Again, here's our advection fog over the Golden Gate where the ocean is warm and the air, I'm sorry, the ocean is cold and the air is warm, and that temperature difference going to cool to the saturation point. And here is where the land is heating up and the ocean is cold. And as soon as it cools at night, that fog is going to go right back from over the water. The fog's going to move back in. Again, here's advection fog over Boston. And I'm going to watch and pay attention to here. You've got to get really good at being able to decipher your Metar. So this Cape PVC, Papa Victor Charlie. So this is Provincetown, Massachusetts, right out there hanging over the fingertips of Cape Cod. So it's an automated report. And again, we have to notice the time. It's not an hourly report because the time here is 0216 Zulu. So it's not an hourly report. We don't know how many times it's changed, but all it's telling me right here, there's mist because the visibility is more than a half a mile. So it's mist. We have few clouds at 1,000, and that's all they're telling me. But look at our temperature dew point. So I'm already a little bit suspicious with basically calm air. Let's go back and do a couple of hours of data and look what happens. This is the one I just showed you, right? And this is what happened in the previous few hours. So we go from 5 miles with few clouds at 3,000, few clouds at 1,000 feet. And then we have 6 miles with a few. And then a few minutes later, we have 6 miles with mist and we have a 300 broken. So this is what I would call that tall fog, that fog just rolling in and out over the coast, that few at 300, few at 1,000, broken, right? And the visibility dropping here over a course of a couple minutes. This is just 4 hours of time right here. So we go from 5 miles to 1.5 miles to 3/4 to a half mile. See, once it goes to a half a mile, it becomes fog, and we go from a broken to 300 over. And now we're pretty much stocked in for the rest of the night. So be very careful about just getting one because you don't know the whole story, okay? Radiation fog, for those of you out in the Midwest, you must be familiar with this. And I'm going to show you a clear indication of radiation fog, all right? That's what it looks like the next morning because it's going to cool over at the same rate. But here is Appleton, Wisconsin. Again, it's not an hourly report, but look at our weather. It looks pretty benign. I get 4 miles, a little bit of mist, but I get clear skies. What could possibly go wrong, right? My temperature dew point is actually 22.7 degrees Celsius, and my dew point is 22.0 degrees. That's the actual temperature. Here's the 23 and 22. But here's the clue right here. Here's the warning flag, is clear skies. It's telling you that radiation fog is on its way. So if you read these, I've got the last few hours reading from the bottom up. We go from 10 miles to 7 to 5 to 4. Clear skies, clear, 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 clear. Boom. Vertical visibility 500 feet, a half mile in fog. And then it drops down to a 1/4 mile in fog. So here is our radiation fog right here. So very quickly in the course of just an hour or two, we go from 10 miles clear to totally stocked in. So again, be very, very careful. Watch the temperature dew point spread and watch the sky condition. Is it clear? If there's an overcast, it's going to lose temperature less quickly. So here's our upslope fog, our adiabatic cooling right here. Here's our valley fog. Why is it going to form in the valley? Answer, because that's where most of the moisture is, right? Valleys, we have our rivers and our lakes. So it's basically the same thing as your, could be an advection fog or radiation type event, but we call it valley fog because it forms there. And then our evaporation fog or steam fog and frontal fog. So here, once again, the lake, this was in the fall, so the lake is still warm, but it's cold at night because of the change of the season. And sure enough, there's all the heat from the warm pond dissipating right into the cool night air. We call it bog fog around here. Okay, Precipitation fog. So when it rains quite a bit, there's a lot of moisture that's raining down on the surface, and sometimes we get a lot of low visibilities from that. And it's interesting. It's as the precipitation, it rains from the thunderstorm, the precipitation hits the surface, and it's usually warm. So that precipitation is going to rapidly want to turn back into a vapor again. So it's that actual water vapor between the raindrops that's reducing the visibility, not the rain itself. It's really interesting. Okay, ice fog or diamond dust. This is what happens when water vapor sublimates right into an ice crystal. We know that from research and researching icing conditions, you know, our severe icing happens between like, oh, maybe like a -5 degrees to a -12 degrees C for most severe icing conditions. But beyond like -20, water vapor can no longer stay at a vapor point. It'll spontaneously combust and turn into, not combust, it'll spontaneously turn into a crystal. So that's ice fog where it's really, really cold. So you up there in the great high plains, you know all about this diamond dust. When my daughter was living in Fargo, one morning she called me, Mom, the sky's sparkling. It's absolutely sparkling. I said, well, how cold is it? She says, it's -14 Fahrenheit. I said, yeah, that's diamond dust. That's because all the water vapor now is ice, and that's why you're freezing. And why are you living in Fargo again? Anyway, so now we're going to go to our stratocumulus. Again, we know about our stratocumulus lenticularis, our standing lenticulars. Again, this is one of the few cloud types that will be put into a Metar. So there's only a handful of cloud types that are put in a Metar, and a stratocumulus standing lenticularis or an altocumulus standing lenticularis will be put in the Metar if they see it. And then if you see that stratocumulus cloud, can you see through it? Yes or no? So you can't see it if it's opaque. You can see through it. Is it wave-like? Are there gaps between? Are there different layers? The duplicatus are in lines. Are they showing you sort of nets? Are there roll clouds? So these are all the very specific types of stratocumulus that you can have. Again, it's our most common clouds. It can be lifted from a foggy layer. It can start off as a cumulus cloud, but it hits that temperature inversion and it can't climb anymore. It'll start to spread out along the sky. So that's our most common cloud, our stratocumulus. And for us, when we see the Metar codes of broken or overcast, they're usually below 12,000 feet, because anything above that would be an altocumulus type cloud. Again, here's some examples of that. We can see the gaps. Sometimes they can rain. Our stratocumulus can have some bits of rain. Here's our stratocumulus standing lenticularis. So we see that motion up in that apparent motion, but you can see that it looks stationary right there. Here's some mammatus clouds, which is downward pouches. So when you look at a mammatus cloud, oftentimes we see them under the anvil part of a cumulonimbus cloud, and that's basically an upside down cumulus cloud. It's a downdraft that's being sucked back up again. So it's getting that cumulus shape, but we're looking at it from the bottom. Some other types. Here's the lacunosus that's sort of spreading out like a fishnet. What this is telling you is there's a lot of humidity in the atmosphere. So this is going to precursor to lower ceilings. So this is probably an advancing warm front that's bringing down ceilings that will eventually give us steady rain, not a rain shower that would come from a cumulus cloud. So that's a lacunosus. So again, for us, it's from the south-southwest. We'll see these fronts move in, these high clouds start moving in. This is a morning glory roll cloud. It's very cool. This particular one forms very specifically in one part of Australia, just a Carpathian Sea, where there's updrafts and downdrafts. And glider pilots come from all around the world to ride these clouds because they're very particular. It's a very unique formation. And they can pick these updrafts on one side and they can ride them for hundreds of miles. And you can see the downdraft right there. I wouldn't want to get caught in that, but certainly on the updraft side, you can ride it for miles. It's really interesting. So here's our alto, our middle clouds. And again, our middle cloud Metar can be an altocumulus castellanus or an altocumulus standing lenticularis. So again, any lenticularis, we know it's turbulence. A castellanus is little castles. So pretty much, unless it's the altocumulus stratosphoris, these kind of going to tell us they're an altocumulus. So there's going to be lifting. Anything cumulus is up and downward lifting. So between 65 and 20,000 feet, mostly water droplets, but you can have ice crystals and you can have both. Oftentimes in thunderstorms and alto cumulus that has a quite of a thick layer to it, it can be both water vapor and ice crystals. And that's where you can get some vicious icing conditions in those clouds. But here's the high alto cumulus, the little puffs. So this isn't not much vertical development here, and we can see through the clouds, but the middle clouds can contain the supercooled water droplets and contain an icing hazard. And again, looking at the shape of the cloud, especially when we get into these big, alto cumulus or the big cumulus type, cumulonimbus type, if there's sharp boundaries, indicates water droplets rather than ice crystals. Most alto cumulus don't will precipitate virga, not anything that's going to reach ground. So here again is a nice middle level alto cumulus. We can see that it's topped off right there. There's not a lot of vertical growth. And of course, these alto cumulus give us those lovely, lovely sunsets. Here's the Castellanus. So it's rising, nothing's capping it. This indicates, if you were on the ground here, it would be windy as all get out if you were standing on the ground. There is a lot of wind coming up. They're trying to grow vertically, but there's a lot of turbulent mixing in the air that's keeping these growing, but they're also shearing it off at the same time. So you'll see this kind of just prior to or right after some sort of frontal passage. So this indicates a lot of turbulence right here. So beware of the ACCs. Again, here's our alto cumulus lenticularis forming over the mountains. They're quite beautiful. What creates these clouds? Any idea? Correct. That there's a hurricane. And a lot of hurricanes, by the time they get further north, we can see they're just they're alto cumulus clouds. They tend to be, when they get up further north, they lose the thunderstorm, the vertical portion of it, and tends to be more of a lower layer, below 25,000 feet cloud phenomena. Of course, they start off as wicked thunderstorms, but as they develop, and then as they dissipate, it becomes more of a alto cumulus type of cloud. Again, alto stratus, we can see the undulating parts. So there's a lot of upper level winds. This is like we see on the beach where the sand is going, the waves are making the sand patterns like this. So we know that there's very strong upper level winds over here. We can see that it's very wispy over here. Again, this tells me that this is probably ice crystals over here and lowering ceilings. Again, if we see a washed out sky behind it, we know there's a lot more water vapor moving in, and it's likely that it's coming in with a warm front. So here we have a lot of different things going on. We have the high cirrus right here. We have some alto cumulus clouds. We have some building cumulus and some low level cumulus. So there's a lot of action going on right here. But these are the wispy clouds. When they're like this tells us, again, there's a lot of motion in the upper atmosphere. Again, they do not have precipitation that reaches the ground, but there's certainly plenty of virga associated. So here's some fibratus. And again, they're described on the shape, whether fibrous or whether they're sort of like a horsetail type shape right there. And they can be quite beautiful. Way cold up here. This is where we're going to get those wonderful sundogs, those really cool optical effects. So here's a high cirrus cloud, and this is actually virga that's sweeping down, but it's being lifted again. And there's another layer of virga. So this is the fibratus, so we can actually see the virga and the downdrafts. So there could be some pretty rocky skies up there, up in the 20,000 types of altitudes over there. So this is looking way up high, the cirrocumulus. And notice that the cumulus bits are really, really small as opposed to a stratocumulus or an altocumulus, which you can actually see the cloud bits. The cloudlets are a little bit bigger, but these are way up high. So you have to look straight up overhead to really see them. Again, the flocus clouds is giving us an example of the type of shape of the cirrus. So we have the cloudlets up there. We have sort of a rain shadow coming in. This is called where the ice crystals actually form and get heavy and do a downdraft. So it makes these holes in the sky. Cavum, I think they're called cavum clouds, C-A-V-U-M. So there's a cirrus stratus right there. We can see some sundogs, there's some halos. This is a 22-degree halo on either side of the sun, and it's reflecting off the ice crystals. So this is definitely a clear indication with, again, with the setting sun or rising sun, you're going to see the halos, and it's a very, very faint rainbow that you can see in this 22, called the 22-degree circumzenith arc. And again, if you see this around the moon at nighttime, you can expect cloudy skies in the morning because that's the high cirrus clouds that are preceding a warm front coming in. And again, here's an alto cumulus versus a cirrocumulus type of cloud. And again, so as the warm mass is coming up behind the receding, behind the back, I should say, the back of the receding high pressure system, we have the beginnings of the warm front, and the warm front starts up high, not at the surface, because we have the high cirrus clouds coming in. And then as the ceilings start to drop, again, the temperature can hold more moisture, and this is where we're going to get those rain showers where it can rain steadily for a day or more. Okay, to get our multi-level or vertical clouds, we have our cumulus congestus. The area has to be unstable. And we all know now what makes air unstable is warming from below and cold air above. There's all kinds of different accessories that we can call, that are attached to these cumulonimbus clouds, and we'll take a look at some of them. Again, if you see a CB or TCU, that's an air traffic controller has to put that in, a tower controller has to put that in because they're trained to identify types of clouds. So that would be a cumulonimbus, a CB, and a towering cumulus TCU. What's the difference between a cumulonimbus and a thunderstorm? The answer is thunder, right? You can have a cumulonimbus cloud, which is a cumulus cloud with rain, or towering cumulus, which is a tall cloud, cumulus cloud. But in order for it to be a thunderstorm or TS, it has to have the thunder part of it. So that's the difference. Thunderstorm has to have lightning. So, and then we can learn all the different lightning types in the remarks section of my Metars, which I happen to have another presentation on my remarkable Metars presentation. So come see me at Oshkosh or at 7 Fun, and I'll be happy to share those with you. So here's some example of of course, the anvil is going off in the direction that it's heading right there. So there's that lifting into colder air, which is making it unstable. All right. The Calvus has something to do with the shape of the top. We can see that it's very fuzzy up here, which means that it's most predominantly ice crystals, whereas down here in these towering cumulus clouds that are forming, it's still water vapor. And here is our haze layer right here. And usually the haze layer can sometimes take place kind of where the lifting condensation level is, not always. And here, how would you like to see that on final approach? Good thing it's a little bit further away. So here we have a capillatus, which is the way they describe that particular top. We still have towering cumulus here. So over here, we actually have all three stages of the thunderstorm. We have the cumulus part of the thunderstorm. Over here, you can't see is the mature, is it raining? And then there's also downdrafts associated with that. And that would be the underside and the mammatus leg. So here, once again, the overshooting top. Here's a cumulus congestion rising. Here's some velum clouds, which is sort of a middle level right here. And here's our cap cloud. This is very similar to a standing lenticularis, an alto cumulus standing lenticularis. It's formed the exact same way, but we call it a cap cloud because it's forming over the top of the thunderstorm right there. And this is a velum cloud. It's just sort of a layer of condensed water vapor, generally about halfway up, but it's not growing. It's just giving us an indication there's an awful lot of moisture right here. I wouldn't like to see that coming up, this sort of wall cloud, this arc cloud right here. So it's called a wall cloud, and you can see the rotation around there. So pretty soon we'll see precipitation, and we could actually see a tuba cloud or a tornado coming in underneath that. So there's a lot of downdrafts and a lot of super saturation right here just before you hit the surface. That looks nasty. I would urge you strongly not to fly into this cloud. Just saying, even if you're working on your instrument rating, this is not what you want to fly into to practice approaches. Again, big thunderstorm. Over here, we have the overshooting top. And when you see the overshooting top, that indicates for us that there's super strong updrafts. It's just blasting through that temperature inversion layer. And we see all the ice crystals over here. So this is a very Don't fly through this. As I like to say, there be dragons and clouds like that. You don't want to get through that there. Do not penetrate the storm clouds. Here again is some fair level cumulus down low, some high level clouds coming in. So chances are there's a change coming along in a major weather pattern here somewhere. So this could be a diurnal heating for the day, and this could be the oncoming of a warm front approaching. Here's some nice iridescent clouds or sun dogs that's going to happen on either side of the sun. The rainbow, these happen at the same altitude, or they're the same line of sight, as we would say, as the sunshine is. And those crystals have to be a particular shape in order to get those colors right there. So again, every time you see a sun dog, it's at the same altitude as the sun. Looks like a bit of a sun pillar right there. Let me go back here. Again, so right here. And then if there's one on one side, chances are there's one on the other side. And here's a glory. The sun is behind us. And there's a very faint, you might see this looking out of an airplane window, or if you're hiking up in the mountains. So this is actually the full rainbow. And so we're actually seeing the shadow of our head if we were climbing, or the shadow of the airplane. And the sun is behind us. Here's some storms up aloft at a couple of way up there at the flight level. So this is what the radar looks like, and this is what it looks like looking out the window over there. So here we're up at, wow, we're pretty high up there, 38,000 feet. We certainly don't want to go through that. So that's before they opted to change their heading and ask the agency for a bit of a deviation, because you certainly don't want to go through that, especially if you're already at flight level 380 and the clouds are way above you. And again, this was the original course right here on the FMS. And so they decided to do a little bit of a deviation, and they're going to sort of cut through this. Again, you can't do this with Sirius XM weather if you have it in your airplane. Don't ever try to pick your way through weather with Sirius XM, because that is ancient history. That is old weather. This is an onboard weather system that's looking out and telling you that's going on right here, right now. So the only way the airline pilots do it is they have the onboard weather. Please, I beg you, do not trust your Sirius XM weather. That is late, and the clouds can go from a puffy little yellow to the mean flashing red in no time at all by the time you get the update. And contrails are not a natural cloud. We'll look at some contrails. They're condensation trails. They were absent after 9/11. I don't know how many of you remember looking out at the sky after 9/11 and not seeing contrails. For me, it was kind of spooky. This is interesting. Look at how the rate at which they dissipate. If the contrail is a bright blue sky and they dissipate right away, it's a high pressure system. It's a dry atmosphere. That water vapor is evaporating really quickly. So it's a dry atmosphere. If the contrail just sort of hangs out there and starts to spread out to a high like cirrostratus cloud, well, you know there's a lot of water vapor in the atmosphere, so it's not evaporating. It's just still staying there as a cloud droplet or an ice droplet. So that's kind of a clue as to how wet the atmosphere is, and if it's still pretty moist up aloft, again, could be indicative of a change in air mass. This is not a chemtrail. Tell your friends who may believe that no, this is not a chemtrail. Just saying. So here's a couple of beautiful pictures that my husband took for me up there flying, and you can see the neat shadow over there. And of course, my favorite kind of cloud is, I call it the Cumulus Airshowmachus excitamus, right there. And I hope you get a chance to see many of those. And here are my resources. Again, the best books you can buy right here is Pilot Weather from Solo to the Airlines by Morris and Deadstead, 2018. Cloud Spotters Guide. And if you want to be a member of the Cloud Appreciation Society, I strongly urge you to look up the Cloud Spotters Guide. Again, there's some other great books out there that I use very often, and these are a few websites. And I hope you enjoy the presentation and keep looking up.